Oh. What was there? Okay. What was supposed to be that one? You like no, actually. Oh. I cannot get that song out of my head. It's up mine.
What was this problem? X approaches what? 4. X squared minus 1. X squared minus 1 over x minus 4. Okay. And then, what was 19? Limit as x approaches infinity.
Natural log of x over x to the 2 power.
Okay. Okay. Now, I guess before we get into those problems, just to review quickly here, what it is we had that we were talking about yesterday. What we're going to do today is we're going to look at these indeterminate forms a little bit more carefully and give you one more tool to evaluate these limits. Find the limits if maybe they don't exist or maybe if they do exist and find what they are. But all of, really, we wouldn't need it. I mean, with what we have right now, we should be able to find about any limit. Now, there are some where, you know, without a calculator or without this other rule we're going to learn, we might not be able to do. But vast majority of limits we should be able to do algebraically or thinking our way through them. Or, you know, we were talking a lot about how big is the top getting versus how big the bottom, and you know, this is getting big faster, smaller, faster, whatever. I mean, with those ideas in mind, we can do about all these. But then we're going to add something to it today. Okay? So, but let's just review that because there's a lot here to kind of keep straight. So, the first thing we talked about, and there's really 2 different types, I think, if we're going to categorize these. The first one is if you're doing the limit as x approaches a number. That's when you're looking from 2 sides. Anytime you're doing x approaches 0 or x approaches 1 or x approaches 2, you're talking about the cars meeting at the same spot. That's the limit. If they don't meet, then the limit doesn't exist. Okay, now these are the different variations of what can happen. It could be the easiest kind where you just do direct substitution, you plug in, you get a number. That would be that first situation. And I always think it's good to picture a graph when you're thinking about limits, even though, you know, when you're doing one of these, you're probably not thinking about what this graph is. Or you're not thinking about what this graph is necessarily. Okay? But if you find a limit, then what that means is somehow the car's met, or there is a value that it is getting close to. Okay? And so that would be like this first or maybe the second situation. If the limit doesn't exist, then there's some reason why, and you should maybe have a sense of what that picture, that graph would be looking like. Okay? So if the limit does exist and you can just plug in a number by substitution and get a value, it would be something like this. What happens that causes this kind of a picture? But I mean, what happens in the equation that makes it, not just dividing by 0, 0 over 0. If you do an evaluation and you get 0 over 0, then that is kind of this situation. But the limit may still exist. And I can jump ahead here a couple pages, and that would look like these 2 things. So here we had a couple of examples where we just plugged in a 1 or plugged in a 2. We got numbers out. Those would have been like this first picture. Okay, right here. No problems. You get a number, there's your answer, there's your limit. Okay? But the second, this one over here, we plug a 2 in, we get 0 over 0. So we called that indeterminate. Something's going on. Now, earlier I'd said when you get 0 over 0, what should you do? Keep going, right? There's more to do. There might be a limit. Well, one of the things we kept going was factoring, some sort of algebra. something where we can cancel the x minus 2. Well, today I'm going to give you another thing you can do if you get 0 over 0 that would also give you the answer. But factoring and canceling is still a good way to do it. And we did ones with conjugates, we did one with common denominator, but they all basically were just algebra techniques where we could cancel so we could get the answer. Okay, so that strategy is still important, and that would be this kind of a scenario. What would an equation look like that would create this kind of scenario? It'd have to be a piecewise function, right? So we haven't really dealt with many of those. Now, I think there are a few on your homework today. But if you get a piecewise function, well, then you just look at the equation that's on the left. Where's that approaching? Look at the equation that's on the right. See where that's approaching. See if they meet. Okay, so that would be a pretty easy one to identify. And if they meet, that's the limit. If they don't meet, we'd say it doesn't exist. And remember, from this point on, it's not good enough to just say does not exist. You need to have more information beyond that. Like, why doesn't it exist? Well, in this case, the limit on the left is 1. The limit on the right is 2. Okay? Another situation where the cars wouldn't meet would be this kind of scenario, where you have a vertical asymptote. Okay? The cars don't meet here either. Okay? But on the left, this one goes to infinity, this one goes to negative infinity. On this one, they both go to infinity, but again, they're not meeting, so we still have to say does not exist, and we have to say why. Again, look on the left, look on the right of A, wherever we're doing the limit of here. And that would be this type of problem right here, okay, where we plug in a 3, we get 7 over 0, and so we talked about that yesterday. If you get 7 over 0, 5 over 0, something like that, you think, hey, that's a vertical asymptote situation. And so what I need to do is say does not exist, but then I have to show why. Okay, so I have to look on the left. So what we talked about yesterday is the way you look on the left is as x approaches 3, you pick a number just to the left, 2.999. And you try that. And on top here, that would be 7. It would actually be a little less than 7, but actually we don't care about that. It's the 0 we're mostly concerned about here. Remember, a 0 really means not a 0, it means getting close to 0. We're talking about as x gets close to 3. The bottom is getting close to 0. But you can get close to 0 in 2 different ways. Matter of fact, in your homework today, there is a problem that deals with this. Right here at 2, this graph is getting close to 0. As x gets close to 2, the y values are getting close to 0. But on the left, they're getting close to 0 from the negative side. So on the left side of 2, we've got some small negative values here. On the right side of 2, we've got some small positive values, right? So when you get 0 right at 2, what we care about is when we get close to 2. Well, from the left, it's the 0 means getting small. It's getting small, but small negatives. On the right, they're small positives. And so that's going to come into play in some of these problems here. But on a problem like this, not a graph, but on one with an equation, we just plug in numbers. So we say, well, to the left of 3, you'd have 2.999 minus 3. Well, that's a really small negative. 3.01 minus 3, that's a really small positive. And so when you take 7 or something near 7, divided by a really small negative, you get a really big negative. Negative infinity. Positive infinity. So this problem right here would be this kind of problem right here. On one side, it's negative infinity. On the other side, it's positive. Okay, so I really want you to make that connection between these different pictures of limits and what you're going to have to do on the quiz, which are these kind of problems. Okay, so the quiz is going to look like this. You're going to have a bunch of, 8, 10, 12, I don't know how many, limit problems that look like this, and all these various different scenarios will come up, and you need to be able to handle. Okay? Any questions about that, just that has been bugging you? Don't be bashful. Let's look at number 21 and a half here. And go through that one, because that's one of those scenarios. So first thing we do is what? First thing we do is substitute. Plug in a 4. We get 15 over 0, which immediately makes you think what? Vertical asymptote does not exist, right? So it's correct to immediately, and not only correct, you need to have that as your answer. The limit does not exist, but that's not enough. It's never enough from this point forward to just say the limit does not exist, okay? We have to say why. Well, in this case, it's as x approaches 4. Well, the reason it wouldn't exist is if the cars come to meet at 4, that they must not meet, okay? Well, why don't they? Well, we'll just check. So as x approaches 4 from the left, and x approaches 4 from the right, I don't think you need to rewrite the whole limit problem. I think this would be good enough. So 4 from the left, that would be like 3.999, for example. So you plug in 3.999. Now again, I don't really care about the 15. You're gonna get something close to 15, be a little less than 15. It's the bottom I really care about, the 0. What's that gonna be? Small negative. 3.999 minus 4 is gonna be a really small negative. And the closer I get to 4, the smaller it'll be. But it'll still be negative because I'm to the left of 4. Less than 4. So it's a really small negative. Well, 15 divided by a really small negative, really big negative, right? 15 divided by a really small negative is a really big negative, negative infinity. And likewise, 4.001 minus 4, so this would be roughly 15 over really small positive. 15 divided by a really, really small positive is a really, really big positive. And so that is your explanation of why this limit does not exist. Okay? Yes.
Would that be sufficient for the AP test?
I don't think, to be honest, this is more for me, not for the AP test, because I don't think on the AP test, remember, on the AP test you got multiple choice, you got free response. And the free response is where you really have to show your work and, you know, do units and all that stuff. There's only 6 of those questions on the AP test. Now they have multiple parts.
They won't necessarily involve limits.
I don't, there are some, there may be, and I'm going to show you a couple here in a minute, but they're all multiple choice ones. There could be a limit problem in one part of a free response question. I doubt you have to go into quite this much detail on it, quite honestly. Okay? Now, I gear a lot of what we do towards what you're required to do on the AP test. However, I sometimes have more. You know, I mean, I mean, the AP test isn't entirely the whole thing we do. Now, that's a good lead-in, though. I've pulled out a problem here from an old AP test that I wanted you to look at. Okay, this question right here. Everybody take a look at this and see if you can answer it. Okay, it's a multiple choice from a recent AP test. If you can't read this, it says the limit as x approaches 2, approaches 3, approaches 4, approaches 5. Okay, which one is it? C. Now, hopefully that would be a pretty easy question for us, right? The limit exists. If you look through here, as x approaches 2, that'd be right here, the limit exists. The cars would meet. There's a hole, the diner burned down, right? It's been moved, whatever, doesn't matter. The limit exists. At 3, the cars meet right there. Now, there's a sharp point there. The derivative does not exist. The slope is undefined there. But the limit exists. The cars meet. Okay, as x approaches 4, that's the one you guys said was false, right? The limit does not exist there. Okay, as x approaches 5, no problem there, the cars would meet. And then it says the function's continuous at 3. And continuous just means you don't lift your pencil, no holes, no breaks, no gaps, right? Any of those things. The formal definition continuous, and we'll have to go back and review this too, but continuous, there's 3 parts, right? Limit has to exist, which it does. There has to be an output at 3, which there is, and they have to be the same. The limit and the output would be the same. Would it be continuous here at 2? Is a function continuous at 2? The Limit exists. There is an output, but they're not the same, right? You have to lift your pencil. There's a hole. It can't have that. So it's not continuous error. So, but that was an actual AP test, and that was one of the questions. Okay? So that's one type that you might see with limit. I got a couple others here we'll get to in a minute. All right? So let's go back. Oops. All right, now here's the new thing that we talked about yesterday then. What about limits as x approaches infinity? Okay, that's different than x approaches 2 or x approaches 3. This is like saying as x gets really, really big. What are the outputs as the inputs get really, really big? Either big positive way out here to the right or big negative way out here to the left. Well, what that really means is a horizontal asymptote problem. That's what really is going on. Okay, that's what a horizontal asymptote is what are the y values approaching as you go, x is way out at infinity or way out at negative infinity. So anytime they ask you for a horizontal asymptote, they're really asking you a limit problem. They're really saying what is happening as x goes to infinity and x goes to negative infinity. Okay, so we talked about some examples, and we talked about how you can even cross a horizontal asymptote, that kind of thing. And it's possible you get a graph that doesn't have a horizontal asymptote or doesn't have a limit at all, like a parabola. Right? As x goes to infinity, these y values just go to infinity. So that's what you would say. Just goes to infinity. Okay? Now you could say does not exist there if you want, but remember, you always have to have something other than does not exist, so you'd say infinity. Okay? It just goes on. And remember, on these problems, there's not two sides. You're not talking about the cars meeting, because you can't get on the other side of infinity. Right? I mean, it's either as x goes this way or as x goes that way. So for it not to exist means it doesn't approach some horizontal asymptote. It just goes off to infinity or negative infinity. Okay? So that's the graphical look, and then we talked about what do some of these actual problems look like. And so we were talking about how fast they grow, that kind of stuff. So we said, all right, x is really big. This would be like 2 billion and 1. Well, the 1 doesn't matter. A billion minus 3, the 3 doesn't matter, right? We talked about that. So this is essentially 2x over x reduces to 2. Or here the x squared. So the high powers we said matter. Okay, high powers dominate when x gets really big. So we did some reducing there. Here we talked about how the top is x squared compared to the bottom is 2x. The top's going to get so much bigger, so much faster, that when you have a fraction, the big, way bigger over just kind of big, that's what you got here. And that's one of the things we're going to talk about today, is not only is 0 over 0 considered indeterminate, but so is infinity over infinity. Okay? So when we get a problem like this one, what we have here is infinity over infinity. If we do a substitution, as x goes to infinity, the top's getting big, the bottom's getting big, we have infinity over infinity. Well, we keep going, just like 0 over 0. So when the top is getting way bigger than the bottom, way faster, that's going to be a really big number, infinity. If you reverse that, if the bottom's getting big way faster than the top, that's going to go to 0. Okay? When the bottom is getting way big, way faster, it goes to 0. So you either get a number, maybe 0, or maybe infinity. All right, now let's look at a couple of examples that are on some old AP tests here of those kind of situations. I've got one here I want you to think about. Let's go to this one. Okay. Here's a problem right here. Go ahead and read that one and think about that. This was from a recent AP exam. Have we got it? What do you think? I think it can only be one.
D would be negative 5. You've got 5 over
I win!
negative.
So you thought it was E. All right, so, okay, I wasn't sure Riley'd be ready, but I think she is, so we'll do the quiz tomorrow. All right, now, prop, I'll be honest, when we get later in the year and we're reviewing, I think these are sometimes some of our hardest problems. Now, right now we're talking about limits and horizontal asymptotes, so hopefully you thought that was pretty easy. Even still, we had several different answers. But most people do not recognize this when they read this question. Most people do not recognize this as a limit problem. And that's what it is. And by the way, this is no calculator, right? So when you hear horizontal asymptote, that is this limit problem right here. What's happening way, way out in infinity when x is getting really big? Well, let's just go through it. It'd be good practice. As x gets really big here, what happens to sine? What's sine do? No. It just oscillates between -1 and 1, which is essentially like being just some number, like a constant. It changes a little, but not much. And then the bottom is what? Getting really big. So you got basically a constant over a really big number. What is that? So this one would be 0. What's this one? 5 times infinity, which is infinity, right? 5 times infinity is still infinity. We're going to talk a little bit today about infinity and different meanings and so forth. What about this one? This one is 0. Infinity minus 5 is basically infinity. 1 divided by a great big number is going to be a really small number, go towards 0. Okay, this one, -5. Now again, what you have is infinity on top and infinity on the bottom, but it's negative infinity. Okay, or probably a better way to think of it is the 1 won't matter. When this is a billion, this 1 really won't matter. This is essentially 5x over -x. The x's cancel, and we get -5. And then this one, again, that high powers dominate, so that really doesn't matter. That really doesn't matter. So we get 20x squared over 4x squared. X squareds cancel, and that reduces to 5. And so it is equal. Okay? So that was on an AP test. We got another one here. Okay. Now, before we do this one, let's talk about let's talk about these. So here we just kind of looked at this situation. Sine of x, as x gets really big, sine is just bouncing back and forth, right? 1 to -1. So it's kind of staying fairly constant. And then the bottom's really big. So a number basically over something really big, that's going to be 0. Here, 2 to the x gets really big and x squared gets really big. So why was this infinity? Bigger, faster. 2 to the x, we talked about exponentials grow way faster than powers do. And so the top gets bigger way faster, so this is infinity. So you had to think about the rate. And of course, we hinted that means derivative is going to be involved somehow here, because derivative measures the rate of a function, rate of change. So the rate that it gets big. So really, when we get into these limit problems with 0 over 0, infinity over infinity, what we're really saying is something getting small over something else getting small. And it's indeterminate because what we need to know is how fast is it getting small, each of them. And the same thing is true here. What we really have is something getting large versus something getting large on the bottom. The key is how fast are they growing and getting large. And so that's how that derivative is going to get involved here. Okay, so we do a problem like this. Now see, on 19, nobody yesterday asked about 19. Now maybe you didn't all get to it before the end of the period, or maybe you just looked it up in the back of the book. I don't know. But I thought this was kind of a tricky one. Somebody want to explain why they got, what was the answer in this one, by the way? Somebody want to explain why this one was 0? I mean, it's not that tricky, but I mean, some people in the art class did a pretty good job, Zach.
Well, I said that to John and Steve that the x to the 2/3 would be infinity to the 2/3, so it's still grow.
It's getting bigger and bigger.
exponentially, and it's going to grow so much faster than the ln of infinity, like natural log infinity.
Okay, and yes, I agree. I just, how do you know that?
Is he smart?
Because he just knows. Well,
We trust him.
okay, you trust him. What's a natural log graph look like? Do we? Am I on the barely? What's a natural log graph look like? I'm hoping we all know that by now, and we really need to. This would be one of those questions where it'd be good to know that. It does grow. Now, do you know what x to the 2/3 graph looks like? Now, you're saying it grows because it is a power, right? And that's true. But here's what x to the 2/3 looks like. X to the 1/3 is the inverse of a cube function. It's the cube root function, right? It's the inverse of a cube function, which is this right here. Okay, it looks like that. Now, x to the 2/3 then would be that squared, right? That would be x to the 2/3. So what's that mean if you square it? What's going to happen? Well, instead of being negative, they'll be positive. So if you were to graph it actually on your calculator, it kind of looks like this, which is kind of cool looking graph. And then the squared thing makes it get bigger a little faster. So it probably goes up faster than what I've got it drawn here. Okay, but it basically still keeps that same shape, kind of like that. So as x goes to infinity, you have this graph that seems to be kind of leveling, but this graph kind of is too, you know. Now, some people, so I guess what I'm trying to say is how do you know for sure that it grows faster? Some people, somebody in their class said they actually typed some numbers in on the calculator. They typed in like 1,000,000 to the 2/3 and compared it to ln of 1,000,000. I think ln, now on the test you won't have your calculator for this, but ln of 1,000,000 is like 13. And 1,000,000 to the 2/3 is quite a bit bigger. Okay, so they tried that for several values and saw that, and that's what happened. But here's what I would like you to think of. Is remember, natural log is the inverse of e to the x. Okay? Natural log is the inverse of e to the x. And remember, we said exponentials grow way faster than powers do. So that means this goes up really, really steep. So what's that mean this one does? It doesn't go up very steep. The reverse of that, it levels. It doesn't actually ever level off. It doesn't have a horizontal asymptote. It'll never level off, but it's growing really slowly. As slowly as this one is growing very fast. And a power then, or this inverse basically of a power, essentially, is going to grow faster than ln will. For the same reason that exponentials grow faster than powers. Okay, so they're both getting big. It's both infinity over infinity. But in this case, the bottom is getting way bigger faster. And so that would be 0. Okay, so that's good. If you got 0 and actually thought of it that way, that's good. Now, the new rule we have that we're going to learn today actually makes this one a lot easier. There's some algebra involved, but at least you don't have to try to know ln x and x to 2/3 and really have to kind of almost guess a little bit, especially if you don't have a calculator.
So, will that work the same way on if we had 2 to the x, or sorry, x squared divided by 2 to the x, would that also be 0?
That would be, absolutely. Because again, the bottom is getting bigger way faster than the top. So that would be 0. Yep. Now, again, assuming this is what we're talking about, right? We're talking about
Yes.
x. Yep. Okay? So, let's look at this one more problem here. This one right here. Okay, this is another one that was on I think this is on one of my practice tests that we'll be working on. We'll have Riley explain this one to us in a minute.
Okay, so,
Or maybe say. And it's which one? C. Right? As x goes to infinity, when will this be 0? It's just like the one Sydney just asked about. For this to go to 0, we need the bottom to be getting big faster. So we need g to be getting big faster. So we look down the list. G, this would not be faster than that. This would not be faster than that. But this one would, right here. E to the x is going to get big way faster than that one is. And the rest of them, 2 to the x, 3 to the x, both get big pretty fast. But 3 to the x, since it has a bigger base, would get bigger faster. Okay? So C. So again, on the AP test, they ask questions. We can learn these different rules, or we can learn these different techniques and so forth. But a lot of times they ask questions in such a way that it's really important to understand what's going on, because they ask them in just a variety of ways to really get at if you understand what's happening. Okay? All right, let's talk about the new rule we have. So you might want to, were there any others in the homework that you wanted to look at? Yeah, Sydney.
Can we look at, well, actually, no, never mind, just consider answer that question.
Okay. I guess one of the ones I was going to comment on was 21. If you just, that's one you can just plug in, right? You put a 0 in, which you always start out with first anyway. Put a 0 in, you get sine of 0, 0, and then sine of that is 0, and that's it. Just 0, right? You just direct sum. Well, yeah, you do. Why did you put? You think it was infinity? Yeah. You do have to be careful, and that is a concern. You know, you're working these infinity problems, and then all of a sudden it says x approaches 0, and then things change. All right, so let's see. I want to do one thing before we do the new thing for today. Turn to page 223. 223. All right. Now, at the bottom of 223, there's a box that talks about infinity here a little bit. And I've been saying to you that infinity's not a number. Infinity's not a number. We can't really treat infinity as a number, but we can kind of think of it as a number as long as we keep in mind it isn't really a number. And what are the differences between treating infinity like it was a number? So the box, they kind of do a good job of talking about that. For example, the first one, 1 over infinity is 0. And they say, that's okay to think about it that way. Now, really, technically, you shouldn't ever use equals when you're talking about infinity, because, again, it's not a number. But what you're saying here is 1 divided by something really big. So 1 or 2 or 3, doesn't matter. Any constant divided by something really big is really small, essentially 0. And that is okay to think about. 3 times infinity is infinity. Yeah. It's like we were talking about 5 infinity earlier, right? 3 times infinity means you're saying 3 times a really big number is just another really big number. Okay? So there are different sizes of infinity, which I've got a little example here to kind of try to get that across. Infinity plus infinity is infinity. That's true, right? I mean, you have an infinite number of things, you add another infinite number of things together, and you have an infinite number of things. Okay? 1 divided by 0 is infinity. Now, in this one, they say, no, that's no good. And the only reason they say that's no good is because you have to think about positive and negative. Okay? In other words, what you have here is 1 over something really small. But the problem is it a really small negative, or is it a really small positive, like problem 21.5 that we did, right? So really, this could be better, I suppose, if you did this. If you put plus or minus infinity, then maybe that would be a little better, okay? And I always use this example with my freshmen, or my sophomores, I guess, now that I have in this Algebra 1B class, when we talk about dividing by 0, okay? You know, why is that an error? Why can't you divide by 0? And I usually say, well, because what you're doing is you're trying to divide by the smallest number. And I give them examples. If you divide by 0.1 and 0.01 and 0.001, you get bigger and bigger numbers. So if you're going to divide by 0, which would be the smallest number, you'd have to get what? The biggest number, right? And there is no biggest number. You can't get it. And that's really what's happening. So when you divide by 0, you really get an infinity. Okay? But there is no number infinity, so that's why it's undefined. Infinity minus infinity is 0. That's not true because, again, different sizes of infinity. We've done examples of that actually already. We talked about x squared minus x. If you do that as x goes to infinity, what is that? What's the limit of that as x goes to infinity? It's infinity. We talked about that yesterday. If you had a billion squared and you lost a billion, you've barely lost anything. You've still got a huge amount. And the bigger x gets, the bigger the difference is between x squared and x. The x basically doesn't mean anything. Okay? So this is still infinity. So infinity minus infinity, the first infinity could be so much larger that it's still infinity. So that's why that's not good. Infinity over infinity is 1. That's not right. We just talked about that. Depends on if it's getting bigger or not. And then the last one is really interesting. And matter of fact, I'm going to add that to my list of indeterminate. 0 times infinity. Okay? So I want you to think of this a minute. 0 times infinity, is that 0? Well, no. You know, we talk about 0 times anything is 0. Well, 0 times another number is 0. But infinity is not a number. When we have 0 over 0, what we really have is something small divided by something small. And we don't know what that is. It's indeterminate. We have to keep going. We have to do something. Depends how fast they're getting small. Here we have something big over something big. We don't know what that is. Depends how fast they're getting big. What about 0 times infinity? Something small times something really big. What's it depend on? How big the big is getting compared to how small the small is getting. And a quick little example, you could do this. Okay? For example, 4 times 4 is 16. Let's let the first one get small and the second one get big. So we'll go 3 times 5. 15. 2 times 6. 12. 1 times 7. 7. So the answer is getting smaller. Getting smaller and smaller and smaller. Okay? Let's do it again. 4 times 4 is 16. Now let's let the first one get small. Let's let the second one get big. Right? Let the first one get small and let the second one get big. Right? Now the answer is getting big. Why? Because the one getting big is getting bigger a lot faster than the one that's getting small is getting small. Right? So we don't know that it's going towards 0 or going towards infinity. It depends. Okay, so that is also an indeterminate situation. All right. Now, what we will do in these situations, okay, what we will do in this 0 times infinity situation is we will rewrite it in one of these situations. Okay? In other words, think of it this way. If I have 0 times infinity, you know the old rule about dividing is the same as multiplying by the reciprocal, right? So one way to write 0 times infinity would be 0 divided by 1 over infinity. Wouldn't that be the same? And wouldn't we just get that saying 1 over infinity is essentially the same as 0? So this would essentially be 0 over 0. So one way to look at it is it's essentially 0 over 0. Or I could do it the other way. I could take infinity divided by the reciprocal 1 over 0. Well, what's another way of thinking 1 over 0? Infinity. So this would essentially be infinity over infinity. So depending how I want to do it, I could take 0 times infinity and turn it into one of those other two. Just by thinking of it that way. Okay. So this is indeterminate. Now, when I was in college, and it's amazing I can remember this long ago, but actually I tell the story every year. So it was, thank you. Okay, so the story goes like this. You've got a hotel, the Infinity Hotel, and it's got an infinite number of rooms. Okay? It's big. Okay? Infinite number of rooms. And we can't get too caught up in the physical components of what this hotel would look like, right? And how long it would take to get to your room and stuff like that. Okay? So that would get us in trouble. But it's got an infinite number of rooms. And it's full. Okay? There's a person in every room. Well, why not? There's someone in every room. There's an infinite. Of course, it doesn't make sense. That's the point of the story, because it's hard to make sense of infinity. That's what I'm trying to get across. There's an infinite number of rooms, and there's somebody in every room, so it's full. And somebody comes to the office and wants to rent a room. And well, no, wait. There's somebody in every room. They can't just go into a room that's already got somebody in it. They don't add one. No, you can't add one. They're not going to. They're not going to put two people in a room. It's not funny. No, it's supposed to make a point. Listen, the question is, how can they? But you're right. If it's got an infinite number of rooms, infinity plus one is still infinity. So they should be able to accommodate this person. They can't say go down to the last room because they would never get there, and there is no last room. Every room is full. So the manager says, we're full, but that's not a problem. We'll get your room. What's he do? Well, he gets on the Infinity intercom system, and he says, okay, everybody move to a room with a number one bigger than the room you're in. Wouldn't that be possible? If you're in room 10, you go to 11. If you're in room 8 million, you go to room 8,000,001. So everybody's in a room, and they all go to a room one bigger. And so what's happened? Room 1 is open. I mean, it starts with room 1 and goes to infinity. So now room 1 is open. So that person goes to room 1. So if 10 people came and wanted 10 rooms, they would all get on the intercom and say, now this would kind of suck, but that's what you sign up for when you go to the Infinity Hotel. So everybody goes to a room 10 bigger than the room they're in. And now the first 10 rooms are open. And so they fit them in. Okay, but here's the kicker. I wouldn't call it a punchline, it's not a funny story, but here's the kicker. An infinite number of traveling salesmen show up. All wanting their own room. So they need an infinite number of rooms. Now they can't tell everybody to move down an infinite number of rooms. They would never get that, right? So that won't work.
Just keep walking.
Can they accommodate them? Now wait a minute. You got an infinite number of rooms. You got everyone full, but you want to add infinity to infinity, which should be infinity. They should be able to accommodate it. And they have to be able to get to their room. I mean, there has to be a room for them to go to. And we won't, again, how long is it going to take them to get down to room 8 million or whatever? Or maybe it's an elevator, very fast escalator, whatever. Any ideas?
Would you have, you just have each person move down over and then move in the person, and then each person one over and add the next person? Or just keep doing it
Well,
forever?
no, here was a thought. Listen up. Here's a thought. Have everybody move to a room one bigger, and then one person come in, then move to another room one bigger, and another person.
That would take forever.
That would take
Literally.
literally forever. So that wouldn't work either. Here's what they would do. No, we're concerned with time. They got to be able to get to the room. They want to go to sleep. But we weren't concerned with the distance that they have to travel to get there. The question is, could they get there? Is there a place for them to get to? Here's what they do. They get on the intercom and they say, okay, everybody is going to move to a room whose number is twice what your room number is. Room 1 would go to 2, room 2 would go to 4, room 3 would go to 6. It wouldn't take forever. Now the question is, would there be a place for everybody? Everybody's in a room with a number on it. No. What I said was, it can't take them forever. What I said was, if there's a room for them to get to, then we're going to assume that they have a speedy one of those walking elevators in the airports or something that goes really fast. If there's a room, the reason you couldn't have it move down an infinite number because there wouldn't be a room there, right? But, right, what rooms would be open?
The odd ones.
All the odd ones would be open, right? If everybody went to a room that was twice what the room they were in, those would all be even numbered rooms, and there's an infinite number of them. Now, some of them would have a long walk. If you're in room 8 million, you're now in room 16 million. I mean, you know what I mean. But there would be a room there for you to go to. all the odd rooms would now be open, and so they could go. Okay. Anyway, he told that story, but it just gets across this idea of infinity and how it's just crazy to think about. And now, yeah, go ahead.
So why couldn't you just like, since it's infinity, hotel, they have infinite rooms, like one section, like just start a new area and then just keep adding and.
Every time it fills up, add another,
No,
build a new
you don't have
infinity.
to.
But you don't need to. That's the
You
point.
don't have to
You don't
move
need to
people.
because no matter what, you can accommodate the people.
You don't have to move people.
You wouldn't have to
the
move
first
people.
person in. Where's the snack machine?
Just gonna build a big.
Yeah, there's an infinite
With an
number.
infinity pool.
All right, one for every
What
room.
if they say they're out of stock?
Can we start doing
All right.
bedrooms then?
Now,
I
one
think this counts.
other thing. So, what's hard to get across on infinity is, and I think about this when I watch the political stuff going on with the fiscal cliff and talking about billions and millions and trillions. And this always amazes me too every time I do it. So if just to think how big these numbers are. I mean, if you have $1 million and you spend $100 a day, how long would it last? Well, get your calculators real quick. Let's just do it. So if you had $1 million, you spend $100 a day. So it'd be 1 million divided by 100 would be 10,000. So it would take 10,000 days, right?
27 years.
And divide that by 365, and it's about 27 years. Now, $1 million seems like a lot of money, right? If you were a millionaire, you spend $100 a day. $100 isn't that much, right? You could find ways to spend $100 every day, I'm sure. You would go through $1 million in 27 years, okay? Now, for me, that'd be all right because I probably won't live that much longer. But you know, for you guys, you might run out of money.
Well, at least 20.
I hope so. That's true. I hope so.
You're not that old.
40 years left?
Yeah, at least.
Yeah.
Oh, yeah.
90? I don't know. I better start getting in shape. But anyway, I'm not 50 yet. I'm darn close to 50.
But you still got it.
I'm-
How close are we?
If we would do a graph, if 50 was the horizontal asymptote, I would be, I'm right along
But it
the
can't be an asymptote because you're
You're
not.
not-
Yeah,
you're not
I'm not
very
gonna-
tall.
I hope I don't top out.
I hope this makes you feel better. You're too young to be my dad.
There you go. That's good. But I don't think so. But
Because my dad's older.
he's older than that. But I could be.
My dad's
All right. So, but wait. Back up. So what do we have? 27 years to spend $1 million at $100 a day. Now, you hear about millionaires, you hear about, Bill Gates and more about billionaires, right? I mean, they're all rich to me. I mean, whatever. Millionaire, billionaire doesn't seem like that big a difference. However, it's a huge difference because how long would it take you to spend $1 billion?
Not that long.
1 million.
273 years.
No.
That would be 10 million. Depends on if you think about like
Well, I'll do it. $1 billion is 9 zeros. Divide that by 100, and then divide by 365. It's 27,000 years. Because, right, 1 million to 1 billion is 3 more zeros. It's 1,000 times as much. So $1 million seems like a lot, and $1 billion seems like a lot. But imagine that. It would take 20 at that same rate that you could go through $1 million in 27 years. It would take 27,000 years to go through $1 billion. I mean, just that alone, and then let alone $1 trillion. I mean, then the numbers start getting big. You can't even think. Yes.
Yeah, it's like if you think about it in like seconds, like 1 million seconds, that was like a couple weeks ago, like a week
Yeah.
ago or so. Like 1 billion seconds, it's like back in the 70s.
Yeah.
Yeah, and a
Well, it
trillion
might even
seconds
be
is-
more than that.
Yeah,
Are there any
Trillion.
trillionaires?
trillion seconds.
No.
So that'd be like
No.
back in the
Say it like that.
Prehistoric dinosaur days.
We don't know over here.
yeah, or trillions of dollars in debt. So
Yeah, I know.
It's
crazy.
And then, yeah, that's true.
No,
The,
it's over
the $16 in I got to admit, the $16 trillion in debt does make me glad I'm almost 50, and not you guys.
It's,
And I don't know what's going to happen to you.
I want to move
But that's true. We enjoyed it in our heyday. Now you guys can pay the bills.
Wait, is Dubai?
All right. Now I told you you'd have time to work your homework, and we're quickly wasting it. So here we go.
You just have to not be
You thought we were done.
Yeah, just don't get
Here we go. All right. Get your notes out. Here we go. L'Hôpital. Oh, does it need an accent or something? Probably. I don't know. Does it have that in the book?
Yes.
Oh, it does.
You don't know.
There we go. L'Hôpital's rule. Some French person, evidently. Okay? Now, this is actually not on the AP test. However, there are problems on there, limit problems, that you can certainly use it. Remember, I said L'Hôpital's rule is just going to be another tool that you can use to evaluate limits. But it's not necessary. But it does make some of them easier. Now, there are some times where it's probably longer to use L'Hôpital's rule. I'll show you an example of each one. But it is just a tool that you can use, okay, if it works for that particular problem. Now, you got to be careful because it doesn't always work. So here's what L'Hôpital's rule says. I'm just going to write it kind of plain English. If you have 0 over 0 or infinity over infinity, that's a very key if. If it's not one of those two situations, then you cannot use L'Hôpital's rule. Okay, so then you would use some of the other stuff we've learned, right? The direct substitution. Well, you always start with direct substitution, okay? Or maybe you just have to reason your way through it. You have to think, okay, is the top big? What's the top doing? What's the bottom doing? So you may not be able to use it. But if you have this, you can use L'Hôpital's rule. Here's what it says. That the limit as x approaches a, or it works as x approaches infinity, it works for both of those, of f of x over g of x. Now remember, it's got to be 0 over 0 or infinity over infinity, so it's some sort of fraction. If you don't have a fraction, then you might have to do what I had up here. Right? If you've got something like this, if you've got a 0 times infinity situation, then you may have to do kind of a reciprocal thing to turn it into one of these. Because it's got to be one of these for L'Hôpital's rule to work. What L'Hôpital's rule says is that the limit of f over g is equal to the limit of f prime over g prime. Now, you certainly don't confuse this with the quotient rule. We're not doing the derivative of that fraction. What we're doing is the derivative of the top, the derivative of the bottom. Why? I've already hinted at it. That's what we've been talking about. When you have 0 over 0 or infinity over infinity, what you're saying is what you want to know is how fast is the top getting small or big compared to the bottom getting small or big. And that's the rate, its rate of change, which is its derivative. So simply do the derivative. And if you do that and you still get 0 over 0 or infinity over infinity, do it again. Do their rates of change. Do the derivative again. Okay? So let's look at a couple of examples. So one of them would be, one example here, let's do, let's do infinity here. Let's do limit as x approaches infinity, sine x over x squared. This was one that was, I think, on our homework, something like this. Okay? So let's say we were confronted with this problem right here. So we would look at that and we'd say, okay, as x goes to infinity, what's sine doing? Fluctuating from -1 to 1. What's the bottom doing? Approaching infinity. Can we use L'Hôpital's rule?
No.
Cannot. You can only use L'Hôpital. So this is one of the mistakes, the common mistakes, once we learn L'Hôpital's rule, is we try to use it all the time. And you can't. You have to first do the same thing we've always been doing here, is you try your direct substitution. Only if you have 0 over 0 or infinity over infinity does L'Hopital's rule apply. If you don't have that situation, then you can't use it. So this would be what for the answer?
0.
0. And so we get that the same way we got it on our homework today, right? So this new thing, this L'Hopital's rule, is not something to be used on all problems. It's just another thing that can be used. All right, let's do another one. Limit as x approaches 2, x squared minus 4 over x minus 2. Okay, so you plug in a 2 and you get 0 over 0. Now, until we learned L'Hopital's rule, we would do what here? We would have factored this and canceled it. We'd have gotten x plus 2 left. We'd have plugged in a 2 and got, no, wouldn't it be 4? Right? Because we'd have x plus 2, x minus 2. The x minus 2's would cancel. We'd have an x plus 2 left. We'd plug in a 2. 2 plus 2 is 4. So we would have done that, and that's still fine. If the quiz on Monday, you have that problem right there, and you want to factor and cancel, go right ahead. Okay? But we could use L'Hopital's rule since we have 0 over 0. And L'Hopital's rule says do what? Go to the top, which is 2x. Go to the bottom, 1. Now what? Now you plug in your 2. 2 times 2 is 4. So that one worked pretty slick. That was a little faster probably than factoring canceling. Actually, they were both fairly easy, but that worked nice. Okay? Let's do another one. So we got limit x approaches infinity, 3x squared minus 7, 2x squared plus x. So what do we have here? Well, okay, right, 3 halves, but it's infinity over infinity, right? Now, before we learned L'Hopital's rule, we'd have done what with this one? High powers dominate, right? Is that what all you guys say 3 halves? Are you just doing that? See, I would say that's faster than L'Hopital's rule here. I would do that. Yeah, if you recognize that, I think that's great. The 7's not really going to matter. The x is not really going to matter. This is 3x squared over 2x squared. Okay, so that doesn't really matter. So this is like 3x squared over 2x squared. The x squareds cancel, and we get 3 halves. I think that's awesome. Okay, but L'Hopital's rule should work, right? Because it's infinity over infinity. So let's do it. So L'Hopital's rule says do the derivative of the top, 6x, over the bottom, 4x plus 1. That's still infinity over infinity, right? So we could do it again. Derivative of the top, 6, derivative of the bottom, 4, which is 3 halves. So it does work. Nice to know that. But it was a little longer actually doing it that way. Okay, so those other things that we have still work. Now, where it does get, there are some where it can be easier, and like I said, I almost think this one might be one of them. This one's harder. Let's do that one that we were talking about earlier with 2 to the x over x squared. This one's also infinity over infinity, right? Now we know the answer to this one is what? This one is infinity, right? Because the top's getting bigger much faster than the bottom, okay? But let's use L'Hopital's rule just for the heck of it, plus it's good derivative practice. So the derivative of the top, 2 to the x ln 2 over 2x. Now as x goes to infinity, this is still getting big, this is still getting big, it's still infinity over infinity. So do it again. Now how do we do the derivative of 2 to the x times ln 2?
3x ln 2.
No,
1 over 2.
no, not 1 over 2. Remember ln 2 is just a number. ln 2 is just a number.
So it'd just be 2x ln 2.
Times ln 2, there'd be, okay. Let's back up here a little bit. This is just a number multiplied times a function, right? What do we do with a number times a function? It just hangs out there. It just sits there, right? So that ln2 is just going to sit there, right? And now what's the derivative of 2 to the x? 2 to the x times ln2. So it'll be 2 to the x times ln2 times ln2. Over the bottom, which is 2. Now, as x gets big, the top is getting very big, and the bottom is just 2. So we have a real big number divided by 2, which is a real big number, which is infinity. So that'd be a case, again, where L'Hopital's rule I don't think helped a lot. It probably made it a little longer. But that's because you guys know, and we've talked about the rates of change of those things. Now, remember the one we had earlier. This will be the last one we'll do. Limit as x approaches infinity of ln x over x to the 2/3. Now, we said that one was 0. But that one's a little iffy. Now, some of you felt pretty good about the fact that ln was not growing as fast as x to the 2/3, and that's why it was 0. But I'm not sure everybody, and we could probably come up with some other functions where we wouldn't be as comfortable knowing which one was growing faster. So let's do L'Hopital's rule, because it is infinity over infinity. Derivative of the top, 1 over x. Derivative of the bottom, 2/3 x to the negative 1/3. Now we need to do some simplifying here. Okay? So how would this simplify? X to 1/3 would go on top. And the 2/3 we could leave on the bottom for now anyway. What about this this is x to the negative 1, right? So it could go to the bottom as just an x. Then what? Well, but I don't think I need to. Can I simplify this? Can I reduce this or do something with this? Right? I mean, can I subtract 1/3, take away 1 is negative 2, so it would be on the bottom. So wouldn't this be a 1 on top and then a 2/3 and an x to the 2/3? Right? Now, there's a lot of algebra here, but I mean, hopefully we can do the algebra. But if we didn't know about the relative growth rates of this, we get to here. Now, again, x gets big, what's happening? Bottom's getting big, the top's just 1, so that's got to go to 0, right? So, L'Hopital's rule would work there. Okay? So, if you get into some of these, it's possible, and that's going to happen on the homework probably, you're going to get into some of those where you wouldn't be able to know the growth rate, the relative growth rates necessarily. But by doing the derivative, they tell you. That's what the derivative tells you, is the rate of growth, rate of change. Okay? All right. So on the homework, let's take the homework sheet. We got about 25 minutes here for your work. Okay? There's a number of problems here listed. First couple are some graphical ones, and then we get into some where you can use, now you can use L'Hopital's rule on any of these. But remember, only if it's 0 over 0 or infinity over infinity. So if you get like 7 over 0, then that's vertical asymptote. You have to look on the left, look on the right, you know, that kind of thing. All right? So all those same rules that we've been learning apply. This is just one more tool to use if you run into 0 over 0 or infinity over infinity. Now I would say at the end there, where it says 56 through 80, the M4 means multiples of 4. So it's really only like every fourth problem, 56, 60, 64. It's only like 6 problems in that section. However, I would say you might want to do a few more than that. Now, you might want to save some to do over the weekend if you're getting ready for the quiz, right? But that section on 56 through 80, that's just a lot of good limit problems with a variety of different outcomes, and it kind of hits all the different things we do. So for tomorrow, for sure, do 56 through 80 multiples of 4, but you might want to do a few more than that, and then as we go along, getting ready for the quiz Monday, I would say you should do all those probably, 56 through 80 at some point before the quiz on Monday. Okay? All right, so you can have the rest of the time to work on it.
Wait, so we still do 3, 5?
Yeah, yes, right. So we're doing that line, 4.2, day 2. Do that line. Yep.
I'm gonna be gone on Monday. I have a college visit.
Okay. You can do the quiz tomorrow or when you get back.
All right.
Doesn't matter. What do you want to do?
We covered everything for
with so far?
Yeah, pretty much. We're gonna have a review sheet tomorrow.
I think we'll do when I get back.
Okay. Because we got the slope field. We'll talk
Yeah.
about those a little bit again.
Yeah, I could come in Tuesday morning and take it.
Okay. Sounds good.
Me too. I was like,
Okay. Oh, I gotta. Let me get this. Let me round up this worksheet that I'm gonna give tomorrow. Okay. So I'll give that to you. And then, but nothing new. So just quiz on Monday.
There any homework for Monday?
Well, there's another packet too, but I don't have it run off yet. It'll really be for Tuesday.
Okay.
So I'll try to get a copy of that. Will you be at school at all in the morning or anything? Okay. I'll try to get that run off and to you by after school if you can find it or something. Okay. Yes, sir.
I leave about halfway through the
Good afternoon, Carney
like
High.
at 12.
Sorry for the interruption.
Tomorrow?
Just wanted
Yeah.
to inform you that the internet is back up and running. Thank you.
Like, do you want me to just wait until tomorrow to get everything?
Yeah. So you're going to leave halfway through tomorrow.
A little less than that.
A little less than halfway through class tomorrow. Yeah, I'd say so.
Can I use the restroom?
Yeah.
What am I gonna miss tomorrow?
So did I. So did I.
So I won't be here at all.
But you'll be here Monday.
Yeah, Monday I will be.
Okay.
But tomorrow I will not. I should be here Monday unless something goes wrong.
Let me
I have to
get
stay in Texas.
Okay. Yeah.
Which I'll be fine with because it's warm.
Let me get
It's
some.
supposed to be 72 there tomorrow, Mr. Clark.
Is that right?
Yeah,
Let
I'm
me,
really excited.
let me get some. Let me get some things run off here.
Okay, awesome.